Assalamualaikum. Hi everyone. Welcome back to my video. We are still in chapter 1, reaction kinetics, but for this video, we're going to enter a new subtopic. 1.2, which is collision theory, and at the end of this lesson, you should be able to A. Explain collision theory, B. Define activation energy, C. Explain transition theory, and D. Lastly, draw energy profile diagram on a reaction. Now, let's take a look what we have today. First, we're going to look on what is collision theory. So, the basic principle of a collision theory, we have two basic principles. The first one, particles, which is atoms, molecules, or ions. Okay, so you need to make sure that you know this is your particles of reactant must collide to form product. So collision must occur between the reactants. So if the reactant does not collide with each other, no reaction, no product will be formed. That's the first one. The second one, products can only be formed when effective collision occur between the particles. So first, the particles must collide, the reactants particles must collide with each other. The second one, it must collide effectively. Okay, so what does effective collision means? By right, when we talk about effective collision, it is a condition when the reactants collide with each other and it will form the products. Okay, so we have two conditions for effective collision, and for this effective collision to occur, it must meet these two parameters. So the first one, activation energy, we're going to look on the activation energy, and the second one, correct orientation. Okay, so what do we have by these two? We're going to look now for the first condition, which is activation energy. So if you look here closely, this is the symbol for activation energy. It is written as capital E and subscript A. So now, what is activation energy? So, a colliding molecules must possess a minimum amount of energy called activation energy. Why do molecules need this activation energy? Because it's the minimum amount of energy needed for the reactant to turn into product. Okay, now, so let's take a look on the next one. So this is just like I mentioned before, the definition of activation energy, minimum energy required to initiate a chemical reaction. So the activation energy may be gained through the collisions of molecules. The energy is used to break the bonds between the reactant particles, and then these atoms will form new bonds in the product. So activation energy, the energy needed for the reaction to be activated, for the reaction to occur. Without enough energy, we cannot produce any product. Even though we supply some energy to our reactants, but if it doesn't meet the minimum energy, if it does not achieve the activation energy, no product will be formed. After we have enough energy, the second condition for an effective collision to occur, for a product to form, it must occur in a correct orientation. So what does correct orientation here means? Okay, a collision must be in correct orientation in order to form product. If the reactants just collide randomly, not on the correct orientation, even though it has enough energy, still we will not produce any products. So what do I mean by correct orientation? So the correct orientation means that the collision of molecules occur at the correct angle that favors the formation of product. So let's take a look on one example. So I have a chemical reaction here, 2HI gas to produce I2 and H2. So my reactants is HI. So the Hi molecules will collide with each other to form iodine and hydrogen. So which orientation can form our product here? So let's take a look. So this is what we call as an effective collision, okay, where reaction will occur. So if you look here, the correct orientation for this one, the structure of the Hi particles, it should be like this, Hi and Hi, and this will be the correct orientation, where here we can produce the product. Our product is H2 and I2. But if the orientation is like this, okay, it's opposite of each other and the two particles collide. So what do we have here? We still have the reactant particles. So this is what I meant by the reaction must occur in correct orientation, must has a correct angle that favors the formation of product. Like for this one, it's not at the correct angle. It does not favor the formation of product. So that's why we still get the reactants here. No reaction occur. Now let's move on to the next part of this subtopic, which is transition state theory. So let's take a look. What is transition state theory? So in this theory, it explains the activation energy as the energy required by reactant molecules to form the activated complex, which is the transition state. The activated complex is a temporary species formed by the reactant molecules as a result of the collision before they form products, and the transition theory is best explained using the energy profile diagram. So everything that I mentioned just now, we're going to look on the energy profile diagram for a clear explanation, for a clear view on what I have said. Okay, so let's take a look on energy profile diagram. Energy profile diagram. So this is our energy profile diagram. So if you look here, for example, I have a reaction here, CH3I plus OH minus to produce CH3OH plus I minus. Okay, so we're going to divide this equation. The left part is our reactant. Okay, reactant. And the right side is our product. Okay, so what is our energy profile diagram? What can we look on energy profile diagram? So if you look here, first the axis. Our axis will be potential energy on the y-axis and reaction progress on the x-axis. And for the axis, it does not have any scale because we just want to look on the reaction progress. Okay, we're going to start with reactants and finish with product. So the things that we will have inside an energy profile diagram, okay, this is what we call as the energy profile diagram. This is the shape of the energy profile diagram, where we're going to start with reactants, and this is here what we call as the activated complex, and down here is our product. So if we look carefully here, our reactant CH3I and OH minus. So the two criteria for product to form, first we must have activation energy, minimum amount of energy for reaction to occur, and then second, collision in correct orientation. Okay, if our reactant here has met these two parameters, we will form product. So if you look here, before it produces CH3OH and I minus, we will have an activated complex here, meaning our reactants will absorb some amount of energy equal to the activation energy to produce the complex, the activation complex, where we call it also as the transition state. So along here, once the reactant absorb energy, what happens? The molecule will bend and the Ci bond begins to break, where the Ci bond is here. Okay, so it will be like this. Our CH. So this is the structure of CH3I. So it will, the bond will bend, and the bond here, the Ci bond here, will start to break. Okay, and then at the same time, it will start forming a new bond with OH minus. Okay, so that's why you will get this activated complex. So once the activated complex is produced, next what happened? The Ci bond here will break and the COH bond will form. Once the COH bond form, we will get our product and also the byproduct, which is I minus. Okay, the next part, to determine which energy profile diagram or what's the shape of energy profile diagram that we're going to draw, there will be two types of energy profile diagram. Okay, what are the types of energy profile diagram? So I give you here a general equation, A plus B to produce C plus D. So where this is our reactant and here is our product. Okay, so I will show you two different types of energy profile diagram. The first one is for exothermic reaction, and then the second one is for endothermic reaction. So how do we know which energy profile diagram must we draw? So it will be based on the value of delta H reaction here. For a chemical equation like this, the one that have a balanced chemical equation and given the delta H reaction, this is what we call as thermochemical equation. Okay, thermochemical equation. And you will see more of this thermochemical equation later on chapter 2. So now, how do we know? We're going to draw this one, or here we're going to draw this one, or we're going to draw this one based on the delta H reaction. So do you still remember what does it mean by exothermic reaction? So from last semester we have learned that an exothermic reaction is a reaction that release energy. And we can identify from a thermochemical equation, it is an exothermic reaction when the delta H equals to negative sign, negative kilojoule. And then for endothermic reaction, so endothermic reaction is reaction that absorbs energy. So it can be identified when you have delta H equals to positive kilojoule. Okay, now what's the difference between an exothermic reaction and an endothermic reaction? It's actually where we start to put our product, our reactant. Okay, so basically, if you look here, for the axis, it's the same. Where the axis here, we have potential energy against reaction progress. Okay, there will be no value on the axis because this is just sketching a graph. There will be no data. The only data that you will have is maybe the question will give you the value of the activation energy and the value of the delta H reaction. If the question gives you the value for the EA and also delta H reaction, you must write down in the diagram. Okay, but if not given, you just label as EA and delta H reaction like this. Okay, so what we will have inside the energy profile diagram, so like I mentioned before, reactant, product, and up here at the peak of the graph is your activated complex. Next, you must label activation energy and also the delta H reaction. Same goes with the endothermic reaction. There exists reactant, product, activated complex, the activation energy, and delta H reaction. So the easiest one for you to label, the activated complex, it will always be at the peak of the graph. Now, the second one, where are you going to start with the reactant? Okay, is it a higher potential energy or a lower potential energy? So if it's an exothermic reaction, meaning the reactant will have higher potential energy. Okay, so it will be up here. Since the reaction will release energy, the product here will have lower activation energy. Thus, this will be the shape of exothermic reaction. For endothermic reaction, okay, the reactant will have lower potential energy. It's a reaction that absorbs energy, so that's why the product here will have higher potential energy, thus giving you the shape of the energy profile diagram for endothermic reaction is like this. Okay, so that's how we get the shape. Next, labeling. So for labeling, you need to make sure that you put your reactants, all your reactants here and all your products here. Okay, later in the example, I will show you step by step on how to draw this energy profile diagram. Next, to label activation energy. So for activation energy, it will always be from the reactant towards the activated complex, toward the highest peak of the graph. And you need to label the activation energy by using a double-headed arrow like this. Okay, you can also do it like this. Okay, arrow like this, and then next to the arrow EA, and then the value. Also accepted, but you need to make sure that it must be a double-headed arrow and it must start from the reactant. So from the reactant side, what you can do is we can extrapolate here for us for easier drawing the arrow, the activation arrow here. Okay, so that's the first one. The next one is drawing the arrow for delta H reaction. For delta H reaction, the arrow must be a single-headed arrow and it must be from the reactant towards the product. Okay, so that's why you have the purple color arrow down here, purple or pink, purplish pink. Okay, so it will be from the reactant towards the product, and then label delta H reaction, and if you have the value, so put the value here. Okay. Next, for the endothermic reaction, it's the same thing. Okay, even though you look at it like it's slightly different because the point where we start our reactants is different. Okay, for the exothermic, it's slightly higher. For endothermic, it's slightly lower. But to label the arrow, it's still the same. For activation energy EA, it's from the reactant towards the activated complex. And for the delta H reaction, it's from the reactant towards the product. So it's the same. Okay, so now let's take a look on a question, on an example on how to draw this energy profile diagram. Now let's take a look on question involving energy profile diagram. For this video, I provide you with two different examples. So now let's take a look on example 1. So example 1. The following equation shows the decomposition of peroxide H2O2 becoming water and oxygen, and given delta H is negative kilojoule. So draw and label the energy profile diagram for the forward and reverse reaction. Okay, so for this question, the first thing that you need to do is identify either it is an endothermic reaction or exothermic reaction. How? By looking at the delta H reaction here. Okay. Sometimes it just give you as delta H. It's the same. It's still a thermochemical equation. So what we have here is delta H negative. So since we know it's negative, we do know that this is an exothermic reaction. So if we have an exothermic reaction, so the shape of the energy profile diagram should already pop up in your mind. So sketch a bit. The energy profile diagram, it will be our reactant will have higher energy, and then activated complex, and the product will have a lower energy. Okay, for this question, it asks you for forward and a reverse reaction. You will draw two separate energy profile diagram. So for the forward reaction, it's this one. The one that you have here, so forward. So here, our reactant for the forward graph, for the forward energy profile diagram, reactant is H2O2, so reactant, and then H2O and O2 is your product. While for the reverse reaction, even though this is not a reversible reaction, but still the question can ask for energy profile diagram for the reverse reaction. Okay, so for the reverse reaction, it will be the other way around, like this. Okay, meaning H2O and O2 will be our reactant for the reverse reaction, and H2O2, the peroxide, will be our product. Okay, and keep in mind, if the forward reaction is exothermic reaction, meaning the reverse reaction will be endothermic reaction. So the graph, the energy profile diagram that you will draw for the reverse reaction will be the one for endothermic reaction. Okay, so let's take a look on how to draw the energy profile diagram step by step. Okay, now we're going to start with the forward reaction first. So first, draw the axis. You have potential energy and also reaction progress. And then don't forget to label your energy profile diagram, because you have two different energy profile diagram right now. So now, after labeling forward reaction, the next thing is for you to put on the reactant and the product first. So I have my two lines here. So since this is a exothermic reaction, so the line for the reactant will be slightly higher and the line for the product will be a bit lower here. Okay, and next, write down the reactants and also the product. So it will be 2H2O2. So you need to make sure that you write everything is given. If the question already give you or with the state, so you need to write down the state, and then it must be a balanced equation. So the question already give you 2H2O, so you need to write down 2H2O. And then for the product, for the product down there, you will write down as 2H2O liquid plus O2 gas. Okay, reactant, product. You don't have to write down this is the reactant, this is the product. Just write down what is the reactant and what is the product. Okay, after that, we're going to draw the curve here to show and then we're going to label our activated complex. So I already draw here my curve. Now the next step is to label the activated complex. So it will be at the peak over here, so I will label it as activated Okay, activated complex. Okay, so the next part is labeling the activation energy, the EA. So like I mentioned before, the activation energy, it will be from our reactant towards the activated complex. So your choice is either you want to label it inside here, or you can also label it outside. So for this one, I want to label it inside. So what you can do is, okay, pardon me, draw some line over here, okay, and then draw your arrow. So I'm going to put my arrow by using green color over here. Okay, so like I mentioned before, you must use a double-headed arrow, so it will be like this. So make sure you draw here using a ruler. Make sure it's level with your reactant. Okay, and then label as EA. So if the activation energy is given to you, so do write down the activation energy, the value of the activation energy. But if not given, then just put as EA. Okay, the next part is labeling the delta H reaction. So our delta H reaction for the forward reaction, so delta H reaction from the reactant towards the product. So the same thing that we did here, you can extrapolate the line here, but do it like this, meaning in line like this, not a solid line. Okay, so let me draw the lines. So I have my lines here, and then the arrow. Arrow must be from the reactant towards the product. So a single-headed arrow going down here from the reactant to the product, and then label as delta H, and then put the value negative. Okay, because it's given to you in the question negative kilojoule. So write according to what's given. Okay, so this will be your energy profile diagram for the forward reaction. Okay, if I write back the equation, the one that we have, the equation will be 2H2O2 gas to produce 2H2O liquid plus O2 gas. Now, for us to draw the reverse reaction, we need to reverse our equation as well. So for the reverse reaction, our equation will be 2H2O liquid plus O2 gas to produce 2H2O2, and the delta H here will be positive since it will be an endothermic reaction. So now let's draw the energy profile diagram for the endothermic reaction, or for the reverse reaction. So here I already draw the shape for the energy profile diagram. Okay, our reactant will be down here since it's an endothermic reaction. So the product is here, and then the curve. So let's label our energy profile diagram. So now our reactant is 2H2O and O2. Okay, so put here 2H2O liquid plus O2 gas, and our product right now is 2H2O2, the peroxide, with gas. Okay, the next part, let's label the activated complex. It will always be on top here. So activated complex. Okay, after this, we're going to label the activation energy and also the delta H reaction. But before that, let me draw the dotted line down here. So for the activation energy, it will be from our reactant to the activated complex. So it will be from down here up to here. Okay, so let's draw. So I make the line slightly longer so that I can use it to label the activation energy and also for the delta H reaction. So activation energy, double-headed arrow from up here. Okay, let me change my pen color, okay, to green. So from the top here, okay, please use your ruler to get a straight line, and then it must touch the line here and label as EA. If the value is given, so you need to write down the value. So since we have two different graphs here, okay, I already label here as reverse reaction, so I can just put as EA here, or I can also put it as EA reverse. Okay, as you can see here, and compare with the one that you have drawn before, the value of EA, the value of activation energy for the forward and the reverse reaction will be different. If you look from the arrow, for the reverse reaction, for this reaction, the value of activation energy is higher compared to the value for the forward reaction just now. Okay, what does this value show? It shows that to form the product is easier compared from the reactant to the product is easier compared to the reverse reaction. It needs a lot of energy. The activation energy, the minimum energy required to form H2O2 from H2O and O2 is more. It's not slightly, it's a lot more. Okay, that's the activation energy. Next, we are going to draw the arrow for the delta H reaction. So delta H reaction from the reactant to the product. So that's why I extrapolate here for me to draw the arrow from the reactant down here towards the product up here. So your arrow going up. Okay, let me try to draw a straight line. Okay, and then label as delta H and put the value as positive kilojoule. For the delta H, if you can compare from the two graphs, the value of the delta H, the number for the delta H is the same. Okay, the only difference is it's either positive or negative. Okay, so that's for the delta H reaction. The value is the same. But for the activation energy, for the reverse and the forward reaction, the value will be different. Okay, so this will be for question number 1. So for example 2, a key reaction in the upper atmosphere, ozone O3 plus atomic oxygen O gas to produce 2O2 gas, a molecular oxygen. So given here, the EA forward is 19 kJ and the delta H reaction for the reaction is negative 392 kJ. So draw a reaction energy profile diagram and calculate the EA reverse. Okay, so let's look again on the information. Given to you, the forward activation energy is 19 kJ. And given the delta H reaction is negative 392 kJ. So if I can put here, okay, delta H reaction, negative 392 kilojoule. So that's your delta H reaction. So since we have a negative value for the delta H reaction, meaning we have an exothermic reaction. So you will be drawing an exothermic energy profile diagram. Okay, so now let's take a look on how to draw. So this is the energy profile diagram for our reaction here, O3 plus O to produce 2O2. And then the delta H is negative 392 kilojoules. So I already draw the shape of the energy profile diagram. It's for our exothermic reaction. So now let us label together. So here our reactant, so O3 gas plus O gas to produce 2O2 gas. Okay, 2O2 gas. That is our product. Okay, the next one is we're going to label our activated complex. Okay, and then our delta H reaction and also our activation energy. Okay, I have my lines here. So for the activation energy, it's from our reactant to the activated complex. Okay, let me choose my green color pen. So our double-headed arrow, and then we will label this one as EA forward. Okay, label as EA forward, so FWD because that's what's given to you, and then put the value because the value is given, so 19 kilojoule. Okay, I actually made some mistake in your notes where I put positive 19 kilojoule for the activation energy. So for activation energy, you don't have to put positive or negative because activation energy, it must be a positive value. Okay, so you don't have to put the sign. So you can cross the sign that I put on your notes. Okay, now the next one is delta H reaction. So from the reactant to the product, so we're going to draw from the reactant here towards the product down here. Oh, I have a very not straight line. Okay, and it's the same for the second attempt. It's okay. Okay, label delta H reaction equals to negative 392 kilojoule. Okay, so I already settled for the first part of the question where it asks to draw the reaction energy profile diagram. So this is the reaction energy profile diagram. The next part is to calculate the activation energy reverse. Okay, so that's why here I labeled it as activation energy forward because on the same diagram you will label the reverse activation energy and calculate what is the value. So you don't have to draw another energy level diagram. The one that we did on example 1, we have two different energy level diagram because the question asks, draw, sorry, I've been saying energy level diagram, didn't I? It's supposed to be energy profile diagram. Sorry for my mistake. Okay, from the example number 1, we have two energy profile diagram because the question asks to draw it separately. Okay, but for this one, it only asks you to draw for the reaction here. Okay, and then calculate for the reverse reaction. But to calculate, you need to show where is the reverse reaction. So for the reverse reaction, basically, it's the reverse reaction lah. Okay, meaning it's from 2O2 to its O3 plus O. So by not changing anything in our energy profile diagram, the reaction will go like this, meaning right now O2 is our reactant and O3 and O is our product. So this is, we can use this diagram, this energy profile diagram, to find the energy for the reverse reaction. Okay, so to find the activation energy for the reverse reaction, since right now O2 is our product, O2 is our product right now, we're going to draw the arrow from, O2 is our reactant. We're going to draw the arrow from O2 towards the activated complex. Okay, so let me draw the arrow for you. So you can draw the line outside here to not make the diagram too complicated. Okay, to keep it simple and tidy, draw the line outside here, and since like I mentioned before, right now our reactant is O2. So to find the activation energy, it's from the reactant towards the activated complex. Our activated complex is still the same. Okay, we're going to draw the arrow. So it's from up here all the way to down here. Okay, again, please make sure you use your ruler for this. And then label this as EA reverse. Okay, we want to find the value of reverse reaction. Okay, the number or the value for the reverse reaction, it will be the addition of this one, the value of the forward reaction, and also the value for the delta H reaction over here. Okay, so the value of the forward activation energy is 19, and we're going to add only the number here, because if you look here, it takes all the value down here. Okay, so plus 392. So here you will get the value for the reverse activation energy as 411 kilojoule. Okay, so this is how you calculate for the reverse activation energy. So, you might wonder, how do we get a reverse activation energy for an endothermic reaction? Just now, we did for an exothermic reaction. To find the reverse activation energy, we add the value of the forward activation energy with the delta H reaction. But how about an endothermic reaction? Okay, so this is the one that we did previously. Okay, so let me put some value over here for our EA and our delta H. Okay, so let's see. I have my delta H as 15 kilojoule, positive 15 kilojoule, and my activation energy, so I will label this as EA forward, okay, as 55 kilojoule. So for the reverse reaction, it will be from 2H2O towards 2H2O. Okay, from here, from 2H2O2, pardon me, okay, towards 2H2O plus O2. So this one here will be our reactant right now. Okay, if we have a reverse reaction from this one. Okay, so to get the reverse activation energy, okay, so let's draw the arrow first. So some lines. Okay, the arrow from the reactant right now, H2O2, towards the activated complex, and label this as EA reverse. Okay, so what you can see here is the value of the reverse activation energy is part from the forward activation energy. It's just some part. Okay, and how to get the value? So you will use this value, the forward activation energy 55, and you will minus with this one, minus 15. Actually, by looking at this, you can look logically why I minus 15, not adding it. So if I add 55 with 15, basically I will get a larger energy. But from the arrow itself, you can see that the arrow for the reverse reaction is actually smaller. Okay, so it needs to be smaller than this value, from the 55 value. So for here, the reverse activation energy will be 40 kilojoule. Okay, you will meet again this energy profile diagram when we look on chapter 2. But for this chapter, this is a very simple calculation, and a simple question that use the energy profile diagram. So we have come to the end of our lesson for this video. For the next video, we're going to enter a new subtopic, which is 1.3, the factors affecting the rate of reaction. So with that, thank you.